This is a pre-built version of the application. So let's go ahead and start the server. And two clients. Now the Diffie-Hellman key exchange method allows two parties, Alice and Bob, that have no prior knowledge of each other to jointly establish a shared secret key over an insecure network. So passive Eve here can see all their communications. So P here is a prime number and alpha is a primitive root modulo P. And Alice and Bob agree to use P is equal to 23 and alpha is equal to 5. And for the purpose of this tutorial, I had the first user that logs in enter those values. So Alice chooses a secret key and sends Bob the calculated public key uppercase A, and Bob does the same thing. He chooses a secret key and sends Alice the calculated public key uppercase B. So uppercase A is congruent to alpha to the power of lowercase a mod b. So we end up with 4 mod 23. And uppercase B is congruent to alpha to the power of B mod P. So we end up with 10 mod 23. Now Alice computes the shared secret key S, and Bob does the same thing. So for Alice, S is congruent to uppercase B to the power of A mod P, so 18 mod 23. And for Bob, S is congruent to uppercase A to the power of B mod P, so the same thing, 18 mod 23. So Alice and Bob now share a secret key, which is number 18 mod 23, and only lowercase a and lowercase b and the computed shared secret key are kept secret, and all other values, so P and alpha and uppercase A and uppercase B are sent in the clear, so passive Eve can see them. Now much larger values of lowercase a, b and p would be needed to make this example secure. And Eve needs to solve the discrete logarithm problem in order to find lowercase a or lowercase b, and then use that to calculate the shared secret key. And for large numbers, this is very hard to do. Next, and before proceeding with the code, let's do a quick introduction. So we will be using the multiplicative cyclic group Z star P, where P is prime, alpha is a group generator, and we have two secret keys, lowercase a and lowercase b, and possible values for those are 2 to P minus 2. So what is a group? What is a cyclic group? What is a group generator? And why do we start here from 2 to P minus 2 instead of from 1 to P minus 1? And how is the concept of a group, cyclic group, group generator, all that related to the discrete logarithm problem? And how is that in turn related to the Diffie-Hellman problem? So a group G with multiplication operation is made up of a set G with binary operation multiplication on G, where the group operation is closed, and that means that if we have A and B in G, then if we multiply those two, we end up with C, which is also in G. And the group operation is associative, and that means that multiplying A times B times C is the same as multiplying A times B times C for all A, B, C in G. And there is an identity element, 1, in G, where A times 1 is equal 1 times A is equal A for all A in G. And for each A in G, there exists an element A minus 1 in G also, and this would be the inverse of A, where A times A minus 1 is equal A minus 1 times A is equal to 1. And a group G is abelian or commutative if A times B is equal B times A for all A, B in G. So now we know what a group is. Next, what is a cyclic group and what is a group generator? So we have this group Z star 13 that starts with 1 and ends in P minus 1 in 12, and we're saying that alpha is equal to is a group generator in mode 13. So if we take alpha to the power of 1, we end up with 2, alpha to the power of 2, we end up with 4, etc. until 2 to the power of 12, we end up with 1. And if we go over those numbers, it turns out that they are this group Z star 13. So alpha is equal to 2 generates this group. And same thing for alpha is equal to 6, 7, and 11. They are all generators of this entire group Z star 13. And now the cyclic part, if we go here, so we start from 2, we end with 1, and then if we go 2 to the power of 13, we start again from 2, and we end in 1 for 2 to the power of 24. And then again for 2 to the power of 25, we start from 2, and for 2 to the power of 36, we end with 1. So this is the cyclic part. We're cycling back through those numbers in this group. Next, let's do a quick proof of the Diffie-Hellman key exchange. So we had both public keys, uppercase A and uppercase B. So uppercase A to the power of B and uppercase B to the power of A, and they both generated the common keys for Alice and Bob, and we want to show that those two common keys are actually the same. So uppercase A to the power of B, it's the same as alpha to the power of lowercase a to the power of lowercase b. And then, so we move A and B together, so alpha to the power of A times B, and then we flip them, alpha to the power of B times A, and then we take alpha to the power of B to the power of A. and so we replace alpha to the power of b with uppercase B, so we end up with this uppercase B to the power of lowercase a. So this one is the same as this one. Now somebody that is passively monitoring the communication between Alice and Bob have to solve the discrete logarithm problem in order to discover the common key that they both generated. And this problem is that given P and beta in Z star P and a generator alpha, what is X, where alpha to the power of X is congruent to beta mod P. And if P is large enough, this is a computationally very hard problem. Now the Diffie-Hellman problem is that we know the generator alpha, the prime number P, and both public keys uppercase A and uppercase B, and we don't know the private keys lowercase a and lowercase b and the common key that was generated, and our goal is to obtain that common key, which is equal to alpha to the power of lowercase a times lowercase b. And one way to solve the Diffie-Hellman problem is to compute lowercase a from uppercase a or lowercase b from uppercase b using discrete logarithm. But it is not proven that solving the discrete logarithm problem is the only way of solving the Diffie-Hellman problem. And we can generalize the discrete logarithm problem so that instead of the operator on that group is multiplication, we can also have addition as an operator. So alpha is a generator and beta is in G, and we need to find X, where beta is equal alpha. This would be either multiplication or addition times alpha, etc. x times. And if we have multiplication, it would be alpha to the power of x, and if we have addition, it will be x times alpha. And addition is what we use with elliptic curves. And next, let's quickly go over why we pick the secret keys from 2 to p minus 2 and we don't use 1 or p minus 1 in practice. And we do that since for G with multiplication operation, we have alpha to the power of 2, alpha to the power of 3, etc., alpha to the power of p minus 1. They generate this group. And if we use the Fermat-Little theorem, we know that alpha to the power of p is congruent to alpha mod p, which means that alpha to the power of p minus 1 is congruent to 1 in mod p. And for a is equal p minus 1, then uppercase a will be equal to 1, and Eve can conclude that the secret key lowercase a is equal to p minus 1. And if for lowercase a is equal to 1, we'll get uppercase a is equal to alpha, and if Eve sees that, she can conclude that the secret key lowercase a is equal to 1. I will start by creating a new project. And I downloaded this package that we will need for doing JSON. So we will go to properties and Java build path, and the code will be in two packages. One for the server code and another one for the client code. Now on the server side we will have two classes, a server class with a main method and a server thread class. That will extend from thread and override the run method, and on the client side we will have three classes: a client class with a main method, and an incoming message, thread class, and an outgoing message, thread class. And those two classes will extend the thread and override the run method. Now the server thread will have a server and a buffered reader and a print writer instance variables, and we will initialize those in the constructor. So it takes in a socket and a server, and we use the socket to pick up a buffered reader. So first we do socket.get input stream, and then we use that instance to pick up an input stream reader, and we use that to pick up a buffered reader. And also we use the socket to get an output stream, and we use that to pick up a print writer. And for the server class, it will be listening for connections on this port and accept those connections with the accept method here. And here we will have a set of server threads for the clients that this server is interacting with. And here we indicate that passive Eve can see all communications on this server. And here we instantiate a server thread for each client, and we put that thread in the set of server threads, and then we call the start method on that server thread instance. And when the operating system decides to execute that thread, it will end up calling this run method. And we will have a get method for the server threads, and we will have this method that forwards the message incoming from one client to the other client. So it checks if this is different than the originating server thread, and it goes ahead and forwards the message. So let's have a forward message method here. And this is the implementation of the run method. So the server will open up the JSON message sent from Alice to Bob, or the other way around. And all what it is doing here is displaying the content of those messages. So P and alpha, and uppercase A and uppercase B for the public keys, and what Alice needs to calculate in order to obtain the common key, which is very hard if the numbers are very big. So this should do it for the server side, and next we'll do the client side. Now here we will keep track of the prime number P and the generator alpha, and the private key and the name, so Alice or Bob, and the public key name, so uppercase A or uppercase B for Alice and Bob, and the public key value. And we will instantiate a client instance, and the server for the purpose of this tutorial is going to be on localhost, and this is the port where the server is listening. And the client will use this class to pick up incoming messages. So the constructor takes in a socket and a client instance, and it uses those to initialize the client instance variable and the buffered reader instance variable. So it does socket.get input stream and use that to get the input stream reader instance, and use that to pick up a buffered reader instance. And this is the class that the client uses to handle outgoing messages. So the constructor takes in a socket and a client instance, and uses the socket to pick up an output stream, and then use that to pick up a print writer, which would be an instance variable. So now going back to the client, it will have two threads for sending and receiving messages. And what remains in this class are get and set methods. And in the incoming message thread, this is the implementation of the run method. So here we're reading the content of the JSON message, and if it contains P and alpha, then we set those in the client instance. Otherwise, if it contains the public key, then we set that public key name and value in the client also. And this handles common key. And in the outgoing message thread class, this method initializes domain parameters. P and alpha. So for the purpose of this tutorial, I had the first person who logs in enter those values. So after picking up those values, we create a JSON object, and we put in it the name of the client, so either Alice or Bob, and the value for P and for alpha. And this method prompts the user for a private key between 2 and P minus 2, and picks that up and calculates the public key and display some messages, and put that public key in a JSON object to be sent to the other client. And this method calculates the common key, so we do that here, and we display it here, and we create a JSON object to inform the other client that we have our common key and we are ready for communications, encrypted communications. And finally, this is the code for the run method. So first we call the init domain params, and then we call calculate public key, and then we call the calculate common key method. And finally, let's go ahead and test run the application. we will have two clients. And this is the first one, and this is the second one. And let's say P is 467 and alpha is 2. And A is 228. And B is 57. So the common key is 206 in mode 467. And let's start two more clients. And let's keep P as 467 and alpha as 2. And let's do A is 3 and B is 5. So the common key calculated is 78 mode 467.